Hello, my name's Arunav, and today I'll be doing Chapter 8, Question 17, and I'm just going to be doing A and B today. Um, so here's the problem. Figure 8-34 shows a pendulum of length uh, L is equal to 1.25 meters. Its bob, which is effectively has all the mass, has speed V naught when the cord makes an angle with theta, it's 40 degrees with the vertical. A, what is the speed of the bob when it is at its lowest position if V naught is equal to 8 meters per second? What is the least value that V naught can have if the pendulum is to swing down and then up to B to a horizontal position? And yeah, so let's look at the work. So for A, it asks for what's the speed of the bob when it's at its lowest position if the initial velocity is 8 meters per second. So here I drew a diagram of it, and you can see h is just the difference in height between its initial position and its lowest position. So here is how you want to solve it. So you find out through trigonometry that h is just the difference between the length and the cosine of that length, as you see here. And you can just simplify down to that equation. And then you use the conservation of energy, which is the sum of the initial and kinetic energy is equal to the sum of the final initial and kinetic energy. So you use those equations, and you can see that you can take out mass, and you also see that the final potential energy is zero because when it's at its lowest position, all of it's just kinetic energy. So you put the numbers in, and you use the equation from above, h is equal to L times 1 minus cosine theta. So you just put the values in, and you get the final velocity as 8.4 meters per second. So now we go on to B, and B asks for what is the least value that V naught can have if the pendulum is supposed to swing from its initial position to a horizontal position. So here you want to set V final to 0 because you want to find the least initial velocity, and you also have the final height as the length because it's in its horizontal position. So again, you use the conservation of energy, and you use these equations right here, and you take out mass, and you basically plug in the values again, and you solve for V naught. And when you get V naught, you have 4.33 meters per second. I also want to add some common misconceptions here. Some people with the height might think the height difference is actually just the entire length of it and just put height as length, which is not true. You have to find the difference in height from its initial position and its final position. And usually when trying to solve pendulum problems, you would want to use the conservation of energy, because that's pretty much the whole point of pendulums, to show that the conservation of energy when it's at and see that like the mechanical energy is always equal to each other no matter what position the pendulum is in. So you usually want to use the conservation of energy.
This problem, you're trying to find out what the initial velocity of the bob on the pendulum will have to be in order for it to do a swing and be completely vertical with the cord still straight. So the first step in this is to recognize that for the cord to be straight, the centripetal force of the bob will have to equal the force of gravity at the top. So for the centripetal force, the equation is mv squared over r, and for force of gravity, it's obviously mg. So you can cancel out the m's here, and then you want to set the final velocity at the top squared is equal to L, the length of the length of the cord, which is also the radius, times gravity. And then you're going to want to set up conservation of energy equation here, where initial kinetic plus initial potential is equal to final kinetic plus final potential. And then you're just going to plug in the values for this, knowing that kinetic energy is 1/2 mv squared and potential energy is mgh. So the next part here is to plug in 0 for the initial height, because we can just set that at 0 for our problem to make it easier. And then you want to recognize that v final squared here is the same as LG as we found in the first part of the problem. So you just plug in LG here. And then the final height will be the length of the chord plus the length from where the bob started to the point of rotation. Okay, and then from here you can just simplify your problem. You know, this is all just 0, so this just all cancels out. And the masses cancel out from all these. And you're left with v initial squared is equal to LG plus 2GL plus L cosine of the angle. And then square root both sides. And then from here you can just plug in the values that you're given from the problem. So in order to solve for initial velocity, you know the length is 1.25, gravity 9.8, again gravity 9.8, and then 1.25 plus 0.25 cosine, and the angle is 40 degrees. So you can just plug this into your calculator and solve for initial velocity. In order to make the full swing and be completely vertical with the chord straight would be 7.451 meters per second. Here, of this problem, we're trying to figure out that if theta increases by a small amount of degrees in parts C and B, how will the minimum initial velocity that's required to complete the swings in these parts be affected? So the first way we can do this is looking at our final simplified equations for the initial velocity in parts B and C, and then we can look at if cosine of 40, which is the angle that we are given, is 0.766, and cosine of a slightly larger angle, 45 degrees, is 0.707. In part B, we will realize that if this part is smaller, then this part here will actually be larger, and so this part will be larger, and if you're subtracting that, then this part will be smaller, and overall your initial velocity here will be smaller. I know it's a little confusing. And then for part C here, if this part is smaller, then this whole part is smaller, and ultimately the whole v initial here is smaller. So but that is one way to do it. Another way to do it is think of it logically, where if you increase the theta, and if this is our pendulum here, it used to be from here, and we increase it, it'll need a smaller initial velocity because it's starting from a greater height here and will swing higher up. So ultimately our answer is that v initial will decrease if theta is in